All right, let's get cracking. Sorry about all the difficulties. I guess this is the first time I'm trying to have this kind of a setup in a classroom, which is why all this is an issue right now. Hopefully, I'll get better at it. Hopefully by next class I'll get better at setting things up. So one thing that I notice right now is that we have about 11 students in this classroom, which means that the others who were supposed to be in the classroom on Monday could have been here. Maybe if we had half of the people from that group show up, we probably would have been okay. So half the classroom right now, or more than half the classroom right now, is open. So we'll try to do some sort of a sign up so that people who really want to come to the classroom can sign up and then show up to the class. I'm really excited to see you guys in a classroom. It's been March, 2020? So it's been quite a while. I have been doing hybrid classes. So I've been doing this for Intro to ECSE, but I suppose you guys have not been doing this much in the last year or so, more than a year. As we get used to in-person classes again, it's going to be a little bit of a new thing, right? Like we are all trying to experience what it was like. So people used to sit close to each other and maybe whisper, maybe discuss what the professor actually means. None of that is happening right now. Hopefully, in the future, all of that can happen. All right. So where were we last class? In the last class, we were talking about some general ideas of computer architecture. Today, we'll be focusing on a life cycle of an instruction. So the key concept that we are going to look at, the basic idea number one, is the stored program computer concept. Let me bring up the chat. So if you guys are going to be asking me questions in the chat, I'm not going to know it. So here. So the idea here is everything is in the memory. All my instructions are in the memory. All my data is in the memory. And then if I execute an instruction on some numbers, on some data, on some operands, I will also store the results of those instructions in the memory, right? So everything is in the memory. So it's going to be our instruction control digital system with a memory. The sequence of instructions are stored in the memory. So what do I need to do? If all the instructions are stored in the memory, all I need to do is point to the first instruction, right? So point to the first address of the memory, wherever that instruction is. And if I do that properly, and if I set up the life cycle in such a way that it executes one instruction, it goes on to the next, it goes on to the next, it goes on to the next, then I'm done, right? I only need to point to where the first instruction is. And there is a specific register that we are going to use for that called program counter. A set of instructions constitute a program. So for example, if you are adding two numbers, there might be a lot more than just one instruction add, right? You may have to bring the operands from the memory to the ALU, do the addition in the ALU, and then maybe if you want to store the results back into the memory, you will have to execute a store operation. The same memory is also going to hold the data needed to execute the program. So for all of this to work without any problem, we are going to assume that our memory is infinitely large. We don't have any constraint on the size of the memory. Now, the next idea that we are going to explore is the life cycle of an instruction. So this applies to all the instructions, no matter what kind of instruction it is. I'll give you guys a few examples. You can have an instruction to add. You can have an instruction to do any of the arithmetic operations or the logical operations. You can have instruction to branch. Right? I'm executing instructions in this part of the memory, and then I suddenly want to branch off, maybe due to some condition satisfying or not satisfying. I may want to branch off to another section in my memory. Essentially, I need to play around with the contents of the program counter in order for me to perform that branch, right? So branching, if I want to stop everything, then there is a halt instruction that I can execute. So if I want to talk to the memory, right? If I want to say bring things from the memory into the registers, then I need to do a load. And if I want to move things back into memory, then I need to do a store. So this is sort of a very quick flavor, giving you a flavor of what the instructions could look like, right? Arithmetic, logic, things with memory, and then halt, branching, so on. No matter what instruction it is, it will have these 5 steps. So the first step is fetch the next instruction from memory to a register. And that register, we are going to call that the program counter. Look for the address of the next instruction to be executed. So what I really like to do when I explain there are two important registers here. One is program counter, and the other is instruction register, IR. So what I really like to do is play a little game here. What's your name? Zach. G. Last name starts with G. Gunther? Okay. Zach, do something. I asked Zach to do something. Zach is going to respond with what do you want me to do, right? Do what? Okay, you asked me to do something. What do you want me to do? So that's obviously the next question, right? What do you want me to do? So let's suppose I have written on a piece of paper what I want you to do, right? I've written it on a piece of paper, Zach. What is your next question? Well, I have the paper right now. Right, so you are going to ask me for that piece of paper, right? I've written the instruction on a piece of paper. I have not given it to you, but you would like to know where that piece of paper is. Because only when you get to that piece of paper, you're going to find out what that instruction is. You're going to have to decode. Maybe I scribbled it in haste, and my handwriting is not really good. So you are going to have to decode that instruction. And once you decode that instruction, you will be able to execute it. Something funny over there? What? Is there a wait instruction if the instructions are being executed quickly? Actually, there is no wait instruction. There is a wait signal that is sent from the control unit to the memory if the speed of access request is coming in much faster than speed of response from the memory. So it is done by the control unit. There's no instruction that get to dictate those terms. The computer architecture is going to dictate that. All right, so let's go back to Zach and the example. We're talking about piece of paper. I've written it on a piece of paper. I've hidden it somewhere. Zach is going to ask me the location of that piece of paper. I'm going to give it to him, right? I'm going to give it, hey, I've stored it over there. I've put that piece of paper over there. Now it's up to Zach, right? If he wants to really execute that instruction, he's going to go find the piece of paper, decode the instruction, and then execute. That's exactly what goes on over here. All I need to do is give the address. That is important. Give the address of the next instruction, and I need to give it in the program counter. We are going to refer to program counter as PC, right? I always go for PC is PC is where everything starts, because that's where you need to look at. So one thing that is commonly sort of a confusion here is the program counter doesn't hold an instruction. It holds an address to the next instruction, right? So don't get confused with that. Now let's go back and check in terms of the number of bits, right? In terms of number of bits, we were saying data is n bits. You guys remember from the previous class, we said data, our data bus was n bits. And we said our address bus was m bits. And then our control lines were C, right? That's what we used in the last lecture. So that's true. I want you guys to tell me what the size is for the program counter. How many bits is the program counter going to be? M bits. That's right. So it needs to be M bits because it's an address. It's not a data, it's an address, right? All right, so that's what? That's our piece of paper, right? Actually, that's not a piece of paper. That's the location of the piece of paper, right? So program counter is holding the location of the piece of paper. What is written on the piece of paper? It is the instruction. Where does that get loaded? That gets loaded into the instruction register. So the register in which you load the instruction itself is called the instruction register, or IR. Now, IR, instruction register, has two fields mainly, two fields in general. The first field is opcode, which means what is the instruction that you want to do? You want me to do addition, subtraction, so there is a certain number of opcode bits dedicated for that. And the number of opcode bits are actually going to dictate the number of operations that your computer can carry out. Suppose if you have opcode bits as 3 bits, then you can only carry out 8 instructions, right? So you're going to need a lot more bits for opcode field in order to carry out more than 8 instructions. So let me show you guys a quick picture of that. Where is it? Right here. So the instruction register, it has this particular format, opcode and then operand specifier. So opcode is a sequence to decode. Like I said, I have scribbled it on a piece of paper. Zach is going to be stressing out. What did he write, right? So he's going to need to decode that opcode to find out what that instruction really is. And then operand specifier is generally an address to the operand. I want you to do it between two numbers. One is already in my data path, and the other number is in the memory. I'm going to give you that address in the operand specifier. So I'll give you the second number, address to the second number in the address specifier field, and I'll tell you what to do with it. Add using the opcode. You already have one number in the accumulator, say in your data path. Bring the other number from the memory, do the addition. That's your add instruction. Can you see that? So instruction register will have two fields. Let me ask you the next question. Where is the instruction register? Where is the instruction? Go ahead. It's in the memory, right? So instruction register is part of the memory. Because we said the basic idea number one, what was it? All the data is in the memory, all the instructions are in the memory. If all the instructions are in the memory, that's where I'm loading them from, right? So the instruction register, IR, needs to be in the memory. Now, can you guys tell me what is the size of instruction register? What is the size of the IR? N? Yeah? N bits for the IR? Because it's in the memory, right? And the memory is n bit wide because that's the data. Addresses are M. Data is n. So my instruction register needs to be n bits. Quick question. N greater than m, n less than m, which one is more reasonable? Or no such criteria needs to happen? N is greater than m. All right. We will be quick. There you go. So the instruction register, which is n bits long, needs to have an address, right? So it's going to have an address for the operand, plus it's going to have opcode bits. So we want at least a few bits for our opcode, right? We don't want that to be less than, well, it can never be less than 0, but we don't want our opcode bits to be 0 or 1. We want that to be a very good instruction set. Maybe 8 bits, maybe 6 bits, right? But we want it to be more than 0. So next question that we are going to ask is, suppose our instruction register is n bits and our program counter is m bits. How many operations can your computer perform? Number of operations that your computer can perform. C is going to be from the control lines, so it doesn't have anything to do with C. C is essentially, the addition of all the load signals, all the output enable signals, all the opcode lines. That's sort of the mastermind of the whole computer system. So C is, we are not going to be talking about C for quite a while. We are going to be in this N and M field. All right, let me go back here. Operand specifier, I said that was M, right? Because it was an address. Yeah? The whole thing was M. Yeah? All right. So number of opcode bits are n minus m. If you have 3 bits for opcode, you can carry out 8 instructions. 0, 0, 0, add, 0, 0, 1, or so on. Yeah. So how many operations can we perform now? 2 to the n minus m. Yeah. All right. Let's go back to step number 1. Fetch the next instruction. Are we done with fetching the next instruction? All right. Well, we are going to have to do a few things to fetch the new instruction, the next instruction that we want to execute. What? First, go look into the program counter. The program counter is going to have the address to the next instruction. Go read the memory. So initiate a memory read sequence. Get the data, which is right now an instruction, from the memory into the instruction register. So PC will have an address. Go read the memory for that address, for the contents at that address, load those contents into the instruction register. That is, once things are ready in the instruction register, you have fetched the next instruction. Step number 1 is complete. Does it change depending on instruction? No. It is always going to be the same thing for all the instructions. Second one is decode. Decode is Zach trying to understand what did the professor write on the piece of paper. What is the computer doing? It is trying to look for 0, 0, 0. You have said opcode is 0, 0, 0. What does that mean? Right? Decoding that opcode field and then consequently sending out all the other control lines accordingly. That's what decode the operation means. 0, 0, 0 could mean addition. or it could mean load, or it could mean store, whatever. It is simply it is a lookup of the code, right? So in a lookup table, you're essentially saying, okay, where does this match? Oh, it matches to add. Let's do add. Because in order to do add, you're going to have to send control signals to the ALU to ask it to do exactly that, add. So second step is decode the instruction. For all instructions, that's going to be the same, right? Decoding the instruction. Yes, sure, you have to do that for all instructions. No matter what that instruction is, you will have to do step 2. Step 3, fetch any operands as needed. And the statement itself says it away, right? It gives it away as needed. For some of the things, you may need to do it. For some of the other things, you may not need to do it. For example, if you're doing add, then you will need to bring a number from memory into your data path so that you can add. That's where you will need to give an operand address. But suppose you're doing halt. If you're doing halt, you don't need to give any operand address, right? You guys see that? Now, an interesting question. If you were doing branching, what would be the operand address for that? If you were doing branching, what would be the operand address for that particular instruction? Branching. So the next instruction, right? So if you want to branch to this particular location in the memory, that location where you want to jump to, branch to, that's what becomes your operand address. You guys see that? So for different instructions, that usage of operand address will change slightly. For arithmetic and logical operations is going to be very straightforward. It is going to be one of the numbers, right? One of the numbers that is part of your arithmetic or logical operation. Next question. So the you need to ask is, where is the other number, right? The other number is already there in you're going to have to do your one at a time. Bring one number from the memory, bring the second number, and do the addition. All right, no questions right now. Move on. Let's see. Fetch any operands as needed. Like I said, step 3 may be applicable for most of the instructions, may not be applicable for some of them. Step 4, execute the instruction. I asked you to branch. I asked you to do addition, add. I asked you to do a logical OR, do that. Do that instruction that you were supposed to do. Who is going to take care of that? Which component in our data path is going to be doing that? Executing the instruction, the workhorse of our computer system, ALU, there it is, right? The ALU is actually going to be doing that particular operation. Shift left, and it is going to be the ALU. Let's see, do internal housekeeping. What does that mean? I'm done with the current instruction. I need to point to the next instruction, right? So I'm essentially going to increment program counter by one instruction. So PC becomes PC plus 1. Now there is a point of confusion here. I want to make sure that you guys get that. When I say PC equals PC plus 1, I'm assuming that 1 is the size of each instruction, right? So in some instruction set architectures, in some ISAs, that might be 32 bits. So 4 bytes, right? So you might see later on in the course, you actually update PC by PC plus 4, because that 4 is 4 bytes. 4 bytes will be the next instruction, because each instruction is 32 bits in Mips. You guys see that? So PC equals PC plus 1 doesn't literally mean just one. It means one instruction. So depending on which instruction set architecture you're looking at, it might be different, right? So usually students, when they see PC equals PC plus 1 in the second lecture, and in the fifth lecture they see PC equals PC plus 4, they are going, which one is it? Well, they're both the same thing. In the first lecture or second lecture, we are talking about the next instruction, plus 1. In the fifth one, sixth one, we are also talking about the next instruction, but our next instruction is 4 bytes away, 32 bits away. So we are going to need to do 4 bytes there. All right. Questions about this life cycle? I think we spent quite a bit of time here. So much so that a student left. Things are not going well for me this morning, huh? Is it? This morning or generally? This morning? Well, right now. Okay, so sorry about that, guys. But I think it's going to be a sad day everywhere, right? So we started 10, 15 minutes late. Things are not going really well. The only good news is that if the recording of this lecture doesn't meet quality standards, I know that I have a recording from last semester that I can provide to you guys. That's the only sort of backup here. All right, structure of a computer. What do we have? We only have generally two things, processor and the memory, right? So these are my two things, processor and my memory. Processor is going to do the job, and memory is going to have everything else, instructions, data, and all of that. But the processor itself can be broken down into two things. One is the control. Control is the mastermind, right? Like the brains. And you have your data path. What is the data path? The worker, the workhorse. So control unit is your brains of the system. Data path is the workhorse. Both combined, that's your processor. And then processor is going to be working on instructions and data that is present in the memory. So we already talked about, the memory system. It's going to have these three things, right? Address. That's the only thing that understands address. And that address could be used for two things. One, I want to read from this address, or I want to write to do this address. Which register will the address go into? Anybody remember that from the last lecture? Which register will the address go into? There are two registers. MAR, memory address register. Very easy to remember, right? MAR, memory address. Which address will it go to? MAR, memory address register. And then data. Go ahead, Meenakshi. Huh? What happened? Will we be able to come to class every day eventually, or will it always be on Monday, Thursday Teams? Eventually, sure. Yes, that's what I'm trying. Also, like I said at the beginning, we only have about half the class full right now. So we might do like a sign up deal so that people who want to come to class can come. People who don't want to can do that. Yeah. Meenakshi, did you want to point that out to me? All right. So what were you saying? Data. Which register will data go into? MBR, also called as MDR. So memory buffer register or memory data register, right? So that's what is used for data. Either being read or you need to store it into the memory. And then depending on the read and write control, right? 1, you read, write, 0, you write. Okay. What does all of this have? Data path. Data path will have registers, shifter, ALU, buses, all of those things are going into your data path unit. In other words, the only thing that is going in the control unit is the biggest finite state machine, right? Main job is what? Well, there are many jobs actually. One of the jobs is to look at the opcode, decode that instruction. The second job is what? Send all the control signals to all the components in the data path. Register, you want to load, send the signal. Register, you want to read it, send the output enable signal. So all of those signals are being sent by the control unit, which is an FSM. Let's see. All right. So we are going to spend quite a bit of time talking about the data path and how it interacts with the memory. Because we need to look at the memory, right? Instructions are there, data is there. So how does the data path do that? We are going to sort of ignore control unit for a while, and then we'll bring that back in as well. So the first picture we will see is the data path unit for a single bus. Single bus, the moment you hear single bus, you know that it is not going well. It is going to be slow. Why? Because there is only one highway connecting everything. Only one guy can write to it at any given time. Things are going to be slow. Things are going to be one after the other, right? Will have to be. There is only one bus. But if we had more than one bus in our system, such as, for example, three buses, then we can do some parallelism, right? We can be moving one thing from one place to the other, maybe an address, and then while in the same time, we may be able to store things in using the result bus, right? Right now, we are looking at a single bus design. So not too good in terms of parallelism. Well, it's bad in terms of parallelism. There's no parallelism whatsoever here. So let's try to take a look at how our instruction is going to work. This is our bus, right? It is sort of the medium with which any register is communicating with any other register. And I'm going to, in fact, treat the bus itself as a register. I'm going to treat everything as a register here. What does PC stand for? The whole class erupts and says program counter. What does it hold? It holds the address to the next instruction, right? Okay, that's over there. That's your program counter. Then we have instruction register here. IR, what does it have? It has the instruction itself, right? Which has some bits for opcode and then some bits for operand. A quick note about IR. I said there are only two fields, right? I said there are only two fields in instruction register, opcode and operand address. It will change depending on which ISA you are looking at. It will change depending on which type of instruction you are executing. So for example, later on in the course, we will be looking at the Mips ISA, right? MIPS. In Mips ISA, there are three types of instructions. R type instructions, I type instructions, and J type instructions. You don't need to remember all of these things, but I want to make this a little bit clear ahead of time so that there is no confusion later on. For R type instruction, the instruction register will have a specific format. 6 bits for opcode, 32 bits for or 16 bits for address. There is a field for function code. There is a field for amount. There are lots of little pieces to instruction register for R type instruction. For I type, it's different. For J type, it is different. So depending on which type of instruction and which instruction set architecture we are looking at, that format of IR will change. Which is why right now we are looking at it as very general, right? Opcode, operand specifier. All right, that's as far as instruction register is concerned. We have another very useful register here. Accumulator, AC. You know what's its function? Its function is to hold temporary results. So for example, while you are doing multiple instructions, you may need some temp, right? Some place where you hold certain intermediate results of your program. You use accumulator for that. Right now, we are showing only one accumulator, but in reality, there are many accumulators because your program will be very complex, so you will need to store multiple intermediate results. But that's what it is for. Accumulator is for temporary storage. What is the size of accumulator? Wait, n, yeah. So it is going to be consistent with the data bus, right? All right. Next, you have the ALU. Now notice, one of the sides of the accumulator is hardwired to the A side of ALU, right? You guys see that? So if you were doing addition, you could have one number in the accumulator and your second number could be in the memory. You load the second number from the memory into the B side of the ALU. The first number is already here, so that gets hardwired to here, and then you add, and then you have the result. You guys see that? So that's the purpose of accumulator, to have one operand ready for the ALU. Our ALU that we are considering has two sides, A and B. Operand 1, operand 2. The result of that ALU is also connected to the bus. And then we have two registers that are going to communicate with the memory. One for address and one for data. You guys see that? They're all connected to the bus. Now let's do a fun exercise. Suppose we wanted to complete step number 1. What is step number 1 in our life cycle? Fetch the instruction, right? Fetch the next instruction. That's our step number 1. Which register should I start looking at first? PC. All right. This is where I'll start. I'm right now over here. Maybe a different color. Right? Program counter is where I'm looking at because that has the address to the next instruction. Where will it go? In order to complete step number 1, the contents of the program should go to what next? Okay, so here, that's a common mistake. So I'm glad that you said it. Program counter holds an address. Instruction register holds an instruction which has opcode. So this cannot go into that directly. Go ahead. Memory address register, because I need to read that instruction, right? Zach needs to find the paper, right? It has, so he still needs to do a little bit of work to get to the instruction. So contents of program counter will first need to move into the memory address register. Through what? Right, but via what? That movement of PC to MAR is happening because of this. Right? And it's a single bus, so nobody else can be writing to the bus right now. Yeah? All right. I'm in MAR. Right now, my memory address register contains the address of the next instruction. Go ahead.
What makes sure that we'll be writing the same time? What just remembers?
Control unit, the brains. The brains are going to say, okay, I'm going to send the output enable for this register. Everybody else output enable is inactive. Right? So the control unit is doing all that. It's like, puppets, and the control unit is making them dance. All right. So now the address of the next instruction is in the MAR. What is going to happen next? We still need to fetch the instruction. The fetching the instruction will end when things are ready in the IR. So after we have a MAR ready, what should we do? Good.
Go to that address in the memory.
And perform.
Move the instruction from
Right. So read the memory. Can I say that? So I want to read the memory now. Address is present in MAR. When I read the memory or initiate a read sequence for the memory, the contents of that particular address location are going to move into what? MBR, right? So now, once I do that memory read, the contents, which is IR, right? Eventually, they need to land into IR. Those are in the MBR now. That's our second next step. From the MBR, where do they need to go? IR. Through the what? Through the bus. Maybe I need to do it here. From here, right? So write to the bus and then bus to IR. Go ahead. Oh, the last step number 5, you mean? The incrementing the program. So we are doing step number 1, right? So all we have done is fetch the next instruction. Zach has the piece of paper. Decoding needs to happen, fetching the operands needs to happen, execution needs to happen, and then we can update the program counter. A lot of things still remaining. But I just wanted to show you guys, how things are going to move. Go ahead.
Because we only have one bus, that's why we can't increment the accumulator, right? Because there's no decode, right? So that's why you have to do this.
Well, so there are two things about that. One, even if we have multiple buses, if you don't have the data ready, you really cannot do it, right? So some instructions allow for that 3-bus design to really use 3 buses. Some instructions, they don't really use that. But if you really want to see the benefit of that parallelism, then you want to Are you guys able to hear me now? Okay. Somebody sent a Bluetooth interfering signal here. All right. Let's see. What are you talking about? Okay. Uh, I think we have talked about a few things. Let's move on to looking at all the possible register transfer operations for this to happen. So what I have over here is a single bus design. We talked about a few things with respect to the single bus design. At least we talked about the size of the registers involved, and to complete step number 1, what needs to happen, right? How does the data move? Now, if you wanted to summarize all the possibilities of movement, data movement, you can summarize them in this way. Now, one thing I would like you guys to notice here is for register transfer, bus is one of the things involved, right? You see this? There is a bus involved here, 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 everywhere here, except for the hardwired connection between accumulator and ALU A side. Everything else has a bus that is going to facilitate that movement. So if you want to go from one register to the other, You've got to go through the bus. So that's one thing that you want to notice. What are these operations? They are all of them. We are just listing out all of the possibilities here. It's not to do a particular thing, it's just listing out all of the possibilities. Now, for example, PC to bus, well, that's going to happen first, right? That is sort of my first thing that needs to happen. What is the next thing that needs to happen? Bus to MAR. What is the next thing that needs to happen? Memory read sequence needs to be initiated. Once you do a memory read, the data gets into the MBR. From it goes to the bus. From the bus, it goes to IR. That's step number one. Fetching the instruction. You guys see that? So we call this register transfer operations, and in this we are also treating the bus as a register. They are all sharing the one bus. Bus is treated like a register. So we are just listing out all of the possibilities here, right? From this to this, all the arrows, they are all sort of captured in that list. Oh, it's not good for parallelism, Richard. It's a single bus design, right? So it's not going to be good for parallelism because bus, there's only one. This is going to support more parallelism. But like I said, some things are going to be, leveraging those three buses. But in some cases, you might not really see the benefit because the data is not ready. So you can at least try to get some parallelism by having three buses. One is called address bus. MAR, PC, and IR. These are the three things that talk address. PC has address to the next instruction. MAR, memory of your address that you need to read or write to. Instruction register has operand specifier, the address of the operand. So you need a connection there. So that particular bus, you're going to call that the address bus. Then there is a result bus. Its main purpose, take the result of the ALU and put it into the MBR so that you can store data in the memory. Yeah? And then there is a memory bus. For MBR, goes through the memory bus and you can load that into the instruction register. Why is that? Well, that's for step number one, right? Step number one is fetch the instruction from the memory. So that needs to happen there. For that, we are going to need the memory bus. We are also using the memory bus to load things from the memory into the ALU-B side to get your second number for that addition. Yeah? So three buses. Now, in some cases, you might be able to do this sort of a pipelining thing. While you do this, you can do this as well. While you are fetching the next instruction, the results of the previous instruction you can be moving into the memory by using the result bus. So three buses, memory, result, and address. Let us do this. What is the size of memory bus? N or M? N. Result bus? Also N. Address bus? M. So I like to kind of do this as we go through. It just keeps us, consistent in terms of, by just looking at this one question, what is the size? You get to understand a bit more about these buses. So I think somebody is not muted right now. I would request you guys to sort of mute over there because I'm able to hear you. All right, next. We are going to add memory now to all of this. Program counter, where is it? Right here. memory address register, memory, instruction register, accumulator, ALUA, ALU, M, wherever you see M bus, that's your memory bus, A bus for address bus, and R bus for result bus. Guys, if somebody is not muted. All right. Memory is n bits wide, and we are saying 2 raised to m words. Do you guys agree with that? Memory is n bits wide, and there are 2 raised to m such words. You guys agree with that? See, the address m bits for address. So using that, you can refer to 2 raised to m such locations, right? If you have 2 bits, then you can talk about 00, 01, 10, 11, 4 locations. You have m bits for address. So you can talk about 2 raised to m words. At each location, you will have a data or instruction, whatever that is, but it has to be n bits long because data is n. Our memory is organized. Each, so let me show it here. Those are n, right? 0, sorry, again 1, 2, 3, 4, blah, 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 n. And there are 2 raised to m such words. Because we are using n for data, m for number of address bits. Where does everything start? Program counter, right? Program counter gets loaded into the memory address register. Initiate a memory read sequence. Get that particular address through the memory bus to the instruction register. Step 1 complete. Step 2, control unit is going to look into the opcode field, is going to decode the instruction, right? So we are going to put in a control unit somewhere over here in the next slide. Step 3, the operands. Now when you fetch the operands, what needs to happen? See, the address of the operand is part of the instruction register, right? The address of the operand is over here. That needs to be fetched. So how is that going to play out? That address is going to, let's see, move into the MAR through that line. We are going to again initiate a memory read sequence. And then when you read that particular operand, that is going to move through the memory bus to ALUB, right? So that's your operand fetch. Then you execute. ALU does that. And you increment the program counter by 1 so that you can do the next instruction. You guys see that? All right. Let me talk about unusual here. Why do we need this? We have not talked about a connection that is necessary between a program counter and an instruction register. Why do we need to do that? Good. Oh, sorry, I can. Jump, right? So jump or branch, whatever that is. Branch to that address if a condition is met or not met. Jump to that address regardless, just jump. Then in that particular instruction, you are actually giving the address of where to jump as part of the instruction. So that's your operand address. That will need to go into program counter. That's what is happening over there, right? So that particular line is to support those type of instructions. Talk about what happens after the ALU does its job. After the ALU executes, you have the result in the accumulator. Goes away, goes straight away. You don't have to do it. Does it? That connection is there, hardwired into the accumulator. So the contents of the accumulator are going to be updated as soon as the ALU completes its job. Who's going to make sure of that? The control unit is going to send the appropriate load signal to the accumulator to accept that data in, so that you can change that register. Okay, let's see. Questions here? How are we doing? I think right now what I'm understanding is things are pretty smooth except for the audio. Yeah? Yeah, the audio is going to, if you guys have any good suggestions, let me know. This did not work, this failed. This usually actually works for me, at least on my Windows machine. But that didn't work here. Did you guys have breakfast? Didn't get anything for me? All right, let's move on. You're going to add control. You see this? We have added that FSM over here. And all the red lines that are marked, those are our control lines. Looking at the opcode over here, sending the operation lines to the ALU, perform addition, perform logical OR, do the branch, and all that. Sending the load and output enable signals to all the registers. All of those are marked in red. So that's your control unit, which is your biggest finite state machines. Everything else is the same, right? Everything else in the picture is the same. In terms of our data path, we are there. Control unit, we just added. Is everybody sort of clear about, you know, the main ideas here? Control unit, what is it being used for? And then the data path, what is it being used for? Things are okay there? All right. How does it work? We are going to trace instructions now. And hopefully, if you guys have been with me so far, this is going to go really easy. It's going to go really well, quick and easy. Let's trace a load instruction. I want you guys to do this. When you hear the word load or store, a bell should ring. We are talking about memory. So load and store are probably the only two instructions that are with respect to the memory. Can you see that? So load is going to be with respect to the memory. Store with respect to the memory. All the others do not have directly anything to do with the memory. Yeah, then one of the operand might be there, right? So you have to probably load to complete a add instruction. You might need to load. But when you hear the word load or store, I want you guys to think about, oh yeah, it's with respect to the memory. Which means that I need to be talking address. All right, so what we are going to trace is this particular instruction. This is the current contents of the accumulator need to get added to some contents of the memory given an address. So I'm going to tell you the address of a particular number, bring that particular number into my ALU, B side. The A side is going to always have the accumulator, add them, store the result back into the accumulator, right? That's what I'm trying to do here. Accumulator plus some number that is present in the memory, and I'm going to refer to that by an address, add that, so addition is the operation here, and then save that result back into the accumulator. So in other words, you don't need to store to memory. You're still storing that result in the accumulator, which is part of the data path unit. That's what I want to do. Step 1, 2, 3, 4, 5. It's going to be the same. First, instruction fetch. How is it going to start? PC gets loaded into MAR. Red line, red arrow there. Next, initiate a memory read sequence. When you analyze in MAR, read that address so that you have the contents read into MBR. Once you have the contents read into MBR, here. Once you have that contents read into MBR, they move into IR. So you see, those three things are part of step number 1, instruction fetch. Your next step is to decode the instruction. Handwriting was bad, need to understand what he wrote. So we are going to look at the opcode bits of the IR. They are usually at the front end of the instruction register. Those instruction bits, in other words, those are the most significant bits of that register usually. Opcode bits are going to be looked at by the finite state machine, which is over here, and then we are going to send the appropriate control lines to the ALU. That's your decoding of the instruction. Next, we need to do an operand fetch, and for this guy, for this instruction, we do need to do an operand fetch, right? Because we know we need this number. The first number is already ready for us in the accumulator. We need to bring it over here through the load path. That's your memory bus. So third step, operand fetch. Move the operand address from instruction register to MAR. So that's there. Initiate the memory read. Once you initiate the memory read sequence, things will get loaded onto the ALU B side. That's your operand fetch. Instruction execute. That's essentially going to be carried out at the ALU, and in this case we are just going to do the addition, right? So data available on the load path over here, data also available from the accumulator on the ALU A side. ALU is going to do the addition, and then move the results of S to accumulator. All of these things are going to happen by themselves. We do not need separate instructions to do these things, right? That is part of that particular step of executing data. Last one, housekeeping, which means increment the program counter to the next instruction. We usually write that as PC equals PC plus 1. And when I say 1, it doesn't really mean 1, it means one instruction. Questions about how it works? Are you guys comfortable with this particular notation? Accumulator, arrow, accumulator plus some address in the memory. You guys are comfortable with that? What does address mean? What does mem mean? What does AC mean? What does AC mean on the left side? You're taking the current contents of accumulator, which is a register in your data path. You're adding that to contents present at a specific address location, and you're storing that result back into the accumulator. Okay, let's continue here. Control unit. So control unit, this is good. This is repetitive now. Mind sending all the control lines to the registers as well as to the ALU so that the data flow can happen appropriately. Now, there are going to be a few things that are summarized or a little bit more abstract, a higher level, and then some lower level instructions. We are going to refer to that as register transfer notation, RTN, or micro operations. So certain operations which we are referring to as micro operations. Those are seeing operations in a very, very detailed way, right? So they are seeing the movement of program counter to bus. Well, I don't really need to, right? So program counter to bus, bus is going to MAR. So when you're talking about the register transfer notation, you may just write PC to MAR. But when you're talking about micro operations, you go one level down. You go PC to bus, and then bus to MAR. Just an example, right? So register transfer is going to be a little bit higher level, and when you look at micro operations, that's going to be a little bit more detail. In some cases, in most cases, you are okay with RTN. And in some cases, you might need to, depending on the question posed to you, you may need to provide the lower level details, micro operations. Those are details. All right. Now let's talk about register transfer notation. And we are going to do that for the same thing, ALU add. On the left over here in red, all our 5 steps are listed. Fetch, decode, operand fetch, execute, and housekeeping. All of those steps are listed all the way on the left in red. To the right of each of them, you have a register transfer notation for each step that is being carried out. So each main step will have multiple register transfers. And for convenience here, we also have some comments all the way to the right. Program counter to MAR. Like I said, I'm skipping over bus, right? It's not a micro operation right now. We are just talking about register transfer notation. PC to MAR, which essentially means contents of PC are moving into MAR. So just note the direction of that arrow. Perform the memory read, and then memory to IR, or you could also say MBR to IR. Does that change for any instruction? Or does that change when you change instructions? Does this change when you go for add or halt or branch or jump? Does it change the first 3 register transfers? Doesn't change. You guys are right. Always. Now in the activity for today, you guys are asked to write the register transfer notation for store instruction. Over here, we are doing a load instruction. So when you guys write your activity solutions, things are going to be pretty similar to the sequence of RTN here with some changes. And you have already done 20% of your solution, which is the first step, right? There are 5 steps. You already know step 1 is going to be the same, right? For load or for store or for add or whatever. Next, instruction decode. What are we doing here? We are essentially comparing the opcode bits with a lookup table entry for add from memory, right? So each instruction, who's going to do that? Well, the designer, right, is going to write a programmer's manual or a reference manual in which they're going to list out. I have designed this computer system in such a way that 000 corresponds to add from memory. 001 corresponds to halt. 010 corresponds to OR, and so on, right? So somebody must have designed it, and they put all of that information in a reference manual, and then the programmers or the people who are writing these RTN, they are going to refer to that. Do we have that for our class? Something like that? A reference manual? We absolutely do. It is Mips reference manual. That's what we are going to call it. Mips is the instruction set architecture that we are going to learn to communicate in, that has a reference manual. It is actually depending on the book. So for me, it's the first page of the textbook. It's green in color. If you have a physical copy, that's where it is present. It has all the details about registers that are involved, uh, formats of R type instruction, I type instruction, J type instruction, and so on. So it has a lot of details. What I'm going to do is, as we get to the Mips conversation, I'm going to upload that particular document on Piazza. And I want you guys to be very familiar with it, right? So it's like a crib sheet for your exams. And for your homework, you will need it everywhere. Just put it that way. So we do have that for the ISA that we are going to learn. All right, we are talking about instruction decode. What are we doing? We are looking at the opcode field and we are comparing that with a lookup table. And the one that we are going to compare it with is add from memory. That is going to satisfy for us because that's the instruction that we are looking at, add from memory. And if that satisfies, then we are going to move forward, right? Then we are going to carry out the next 3 steps. How is that going to change for you guys when you write your solutions to activity 2? Instead of comparing this with add from memory, you'll be comparing it with code for store, right? So you will be changing that to store accumulator or whatever that instruction is in your activity. All right, next, operand fetch. What are we doing here? We are moving the contents of the operand address, which is part of the instruction register, into MAR, and then we are performing a memory read sequence. That is the operand fetch. Instruction execute. Of course, this is going to change for your instruction, right? It's not your add from memory, it's something else. So of course, it's going to change when you write it for the instruction in activity. But essentially, what is going on? One of the numbers was already present, accumulator, that's already there. I don't need to bring that. But the second number, which is in memory, I'm going to need to bring that into ALU B, the second input for the ALU. Accumulator is transferred into ALU A. Both numbers are ready. Do the addition. And then the result is available on S, and that goes into accumulator. Maybe different for the instruction that you carry out. Last one is PC plus 1 gets to PC. So we are incrementing program counter by 1 so that it points to the next instruction, and then lather, rinse, repeat, right? It's going to keep doing that cycle. Questions here? How did we write that read, the register transfer notation? So there is no one perfect answer for these kind of questions, right? So for register transfers, for example, if you wanted to say PC to MAR, sure, that is only one right answer. But for things like this, memory read, memory over here could have been replaced with MBR, right? Instead of saying memory read, you may have said initiate a memory read sequence. So things of that nature, you might express them, you might write them in a slightly different manner, but they should convey the same meaning. Okay. Let's do a couple of examples here. Actually, we are doing the load example, and if I remember correctly, store is the example that you guys are working on. So when I say load, I'm moving from memory to register, right? From memory into accumulator. The mnemonic for this load is load accumulator A, LDAA. It stands for load accumulator A. Why the need to say accumulator A? Is there a B? Yes. In some data paths, you will have more than one accumulator. You may have accumulator A, accumulator B, and so on. And if that is the case, then you can bring things from memory into accumulator A, or you can bring it to accumulator B. Right now, we are doing it for accumulator A. There's only one accumulator is what we are going with. So our goal is what? look at an instruction which helps you bring something from memory. I'll give you the address, but go read that address, bring that data into the accumulator. Maybe you want to do some addition with that or something else with that, but that's what you want to do. Load something from memory into the accumulator. And load generally means that, right? Load means from memory into your data path, right? And then store is the opposite. I'm done with the execution. Here is the result. Put it into my memory. I'll give you the address to store. Put it into memory. So store is store accumulator A. Contents of accumulator are going into an address. So the other direction. So we are going to use the 3-bus design to trace all the details about load accumulator A, and then you guys will be working on the store instruction. That's your load accumulator. Step 1 didn't change. Instruction fetch is going to be the same for all of them. PC to MAR, memory read, MBR to IR. No problem. This would be a very good time to let me know if there are any sort of confusion with the first 3 register transfer notations that we wrote for instruction fetch. Any confusion there? Why are these registers? What is the size of these registers? Why are these at the very beginning of our program or instruction? No? All right. Next, instruction decode. Like I said, earlier we were doing addition. So we compared our opcode with add from memory. Now we are doing loading. So we are comparing our opcode bit of the instruction register with load from memory. So a programmer, a designer, is going to write up a manual in which all the details are going to be for opcode. The user who is writing these instructions will need to be careful. I want to do load, so I need to use these particular opcode bits. And like I said, for Mips, when you guys are going to be doing that, you are going to say, oh yeah, here is my instruction. The opcode in hex is for load accumulator, I don't remember, maybe 2 or 3. So look at that particular hex symbol, right? So our reference manual is going to give us all those details. Let's see. So once we have decoded that instruction as load, then we are going to do the next 3 steps accordingly. Operand fetch becomes instruction register has an address for the operand, right? That's probably the number where you want to read from, right? You want to load to the accumulator, right? From where? From the memory. Tell me the address. I've given you in the instruction register. So that particular address gets into MAR. You will initiate the memory read. Memory read, contents of that location will go into MBR. Now MBR is ready with your number. The instruction execution here will be those contents, when they move into the accumulator, you're done with the instruction. And then you do the housekeeping and done. PC equals PC plus 1. Questions here? Can you guys tell me a few things that might change if you had to do a store, which is sort of the reverse process of this? Can you guys tell me a few things that might change here?
So you would reverse what you're doing instead of fetching. You would probably first have to tell the memory where you have to put the address you want to put it in, and then you have to load the MBR. So it's just like switching those 2 steps.
There it is. So this is going to change. From memory is going to change to store to memory, right? And then when you do the operand fetch, you're not actually doing the, you have that address, right? That address will move into MAR. But what do you need in MBR to execute? You need accumulator to go into MBR, right? So you will need to do a MBR to accumulator, accumulator to MBR and then do the memory write. That is going to be your execution for store. Can you see that? Yeah? Yes. Okay. So activity 2 is going to be for your store accumulator, but I guess a lot of hints here, right? Like, so you can take a lot of things from here and change a few things like we just discussed. So that's going to be for your activity. Let's see. A little bit about micro operations.
May I ask a question?
Oh, go ahead.
Okay, so in the 3-bus design,
Yeah.
the accumulator doesn't have a path directly to NVR, so that's to the LU.
Oh, this guy?
Or no, I mean, we go to the LU. Because, okay, if we go down to then, what is it? That when we have the controller, it appears to have us going to the NVR directed. Do you see what I'm trying to say?
Let me see. So here is the store path, right?
Yes.
Yeah. So,
But in the 3-bus design, it doesn't seem to have that path.
oh, it's not being shown as one line, but it is sort of represented in a slightly different way. Let's see. When you're accumulator, you're writing to the accumulator from the result bus, and this is shown this way. Like it's sort of represented in a bidirectional. That was supposed to be a bidirectional arrow.
Thank you, sorry.
No problem. Let's see. Okay, some micro operations. Like I said, there are some operations only when necessary you might have to explicitly mention. For example, things with bus, right? PC to bus, bus to MAR. That's where things start. In some cases, you just can avoid that. Some examples of micro operations are add. Where do you have that? Well, I'm always doing PC equals PC plus 1, right? In some cases, you may not need to do that. You may not need to do that as an addition. You may just need to do that as a micro operation. You are going to do that addition by 1 all the time. Pass B. What does this mean? Sometimes what you may need to do is, let me show you here. You may need to load something from memory and then do nothing to it, go into accumulator. So suppose you had two numbers, right? N1 and N2. Both of them are in memory and you need to add them. What do you do? Let us do an interesting example here. Suppose you have N1 and 2 in memory. What you need to do is S equals N1 plus N2, and you need to store S in memory. What do you think you need to do here? You need to bring, go ahead.
Well, first you have to load the accumulator with N1.
Yes. So load accumulator A with N1, right? What's next? Or to avoid confusion, I'll just say load. Load N1. What do next?
Load N2, load the NVR.
So load N1, right now N1 is, now I need to do addition from memory. So when I do the addition, one number is already ready in my accumulator, N1, I have loaded it. The other number I'm going to bring it from memory, right? Okay, I'm done with the addition. The answer went where? Accumulator. So it has already overwritten my N1. What do I do? So I do load, Then I do add. What do I do next? Store. Store accumulator where I'm going to give it an address to do it, right? So load, add, store. 3 instructions to carry out that. Bring things from memory, do the addition, and then store it back. Can I see it? Accumulator to instruction decode. Oh, earlier maybe. 9 minutes ago. Oh, shoot. All right, sorry, I missed that, Arham. So in those situations, you will have to pass B, right? When you're loading things from memory into the accumulator, you will just pass B because loaded it, don't need to do anything there, right? Loaded it to the ALUB side, pass it, and then it goes to the accumulator. I don't need to do anything with the A. Go ahead.
So why would you do it that way? Why would you pass it to the ALU? Why would you not just have a separate line that goes straight to the AC from the MBR?
From the MBR to AC? Well, I have one accumulator in this design, right? So I want to use that as a place for temporary storage. If I had the ability to sort of do it from A and B together, then I'm sort of hardwiring them both, right? So think of it like this. The purpose of accumulator is to sort of hold things in one hand while you are moving things on the other hand. This is sort of doing the work.
Yeah, no, I understand that, but why do you have to pass that data through the ALU? Because that's just another instruction with the ALU panel, which just do nothing to the. Do you see what I mean? Like we have the store path that goes right from the AC back to the MBR, but you could go from the MBR straight to the AC. Why do you have to go through the ALU? I mean, I understand that that is a path, but it just seems like it's another step.
All right. So when you're doing the load path, there it is. How do you get to AC?
Exactly, that's what I'm saying. That's why I'm wondering why there isn't a path that goes directly from. There's a load path that goes right to B.
Right.
Why should it not also just go to AC, like directly?
Oh, that's just the way how it is set up.
Oh, okay.
Just so you could, and then you could use those kind of connections wherever necessary, but you try to make the common case fast, right? You're trying to make the common instructions that are going on. You're putting the resources over there. Remember, if increased functionality comes at cost, so you don't want to. Sure, you could make a few more changes, maybe have more connections, but there's always like that trade-off. Can you do it with limited number of instructions, all of the operations that you have, or not? Right? That's sort of where it comes down to. Oh, you are fine, man. Let's see. What were we talking about? Right. What is this for? Zero update to PC. Well, if you, in most cases, you may want to start the instructions at the address 0, right? All the way at the top. That's for that, micro operation for that. Updating program counter by 1. That's another micro operation that is written out over here. But some others may require multiple controls operation. For example, PC to MAR, that's a RTN. It's no longer a micro operation. So depending on whether you are explicitly asked, write out micro operations. Until then, you don't need to worry about them. So things like PC to address bus, don't need to write it. Let's see. Yeah, so here is an example of the first step in the instruction cycle, which is instruction fetch. On the left, you have the register transfer notation. On the right, you have micro operations. So the movement of data from program counter to MAR is literally, in terms of micro operation, PC to address bus and address bus to MAR. More details. And similarly for memory read, what does that mean? Memory read is you had one control line for the memory system, write a 1. 1 means read, 0 means write. You're trying to read. And then memory to IR or memory buffer register to IR is in terms of micro operations MBR to memory bus, and then memory bus to IR. So one thing that you can notice is, in most cases, when you are going for micro operations, you are referring to the bus, one of the three buses, right? And when you're talking about register transfer, you're doing exactly that, register to register transfer. Essentially not treating the bus as a register in that case. Questions here or there? Oh, that was when, yes, I remember that. All right. This is your full program in microcode for the load instruction. Are we doing load here? Yes, load from memory, right? Load accumulator with what? I'll tell you the address. Go look at that address. Bring the data from that to accumulator. That's what the instruction is over here. And we are writing the full program of that, which means including the microcode. We already talked about microcode for one. There's no real difference in terms of decoding. Operand fetch, we are explicitly saying that we need to make that particular read one so that we can do the memory read. And then you have all the other things. Here you see ALU pass B. That's exactly how you write that. After you move the memory contents into through the load path into the ALU B side, you do that ALU pass, which means don't do anything to that number, just pass that to the result side. So ALU pass B is what we use for load accumulator. Let's see. All right. We have about 20 minutes left for the class. I'll let you guys work on the activity. Of course, I'll be here. If you guys need to get my help in the classroom, that would be new. And you know, I'll be walking around. For those of you who are online, you guys can put some messages in the chat box so that I can help you with that over there. All right, activity time. I'll stop the recording here. The one thing that I would like to point out is have a good break. We are going to meet on Wednesday, right? Next time we meet is going to be on Wednesday of next week. We don't meet Monday, we meet Wednesday. So we are going to have back-to-back classes on Wednesday and Thursday of next week. So try to relax during the long weekend, and then we'll do the 2 day of classes, and then we'll get back into schedule of Monday, Thursday. So have a fun break is what I'm trying to say. In general, I say next Monday. Yes, you're right, Arham. Wednesday will be Monday schedule. Let's see. Is this a general ISA or something? Oh, this is very, very general. So this conversation that we are having right now, you could apply that to any ISA. But from class 4, 5, we will be focusing only on the Mips ISA. But right now we are talking about things that are very, very generic. As generic as they can be. Oh, wow. All right, so let's see. I'm going to go here and stop recording here. Oh my gosh.